in how many ways can a dance be arranged for unmarried couples in such a way that no husband will dance with his own wife? And the permanent function appears here immediately as a counting function, because this number will be nothing but the permanent of the following matrix. This zero diagonal will correspond to the fact that husband and wife will not dance together. And the other variants are nothing but the transversals in this set. And the number of transversals is exactly the permanent function. The number of non-zero generalized diagonal. And in this way, in fact, this combinatorial number can be computed exactly. Or assume we have a round table, and we would like to put these married couples to sit together. And the question is, in how many ways can we put them, can we place them on the round table in such that man and woman will sit in alternate places, but no husband will sit on the either side of his wife. Again, another combinatorial number, and one answer will appear as a permanent of the following numbers. Here, J M is matrix of all ones, identity matrix, and permutational matrix corresponding to this permutation. The bracket is missing, but doesn't matter a lot. Number of Latin squares, or Latin rectangles. So, no line, row, or column will contain the same element in the Latin. And again, we are interested in finding the quantity of Latin squares. And this is important combinatorial number, and it's still there are many results in this direction. So some of these numbers are computed here. But again, permanent will provide quite a good bound on the number of reduced Latin numbers. And here is the formula. I will not go into the details. Probably the last combinatorial configuration is a domino type. So you have a chessboard, and you would like to tile in dominoes. So two squares of different colors, black and white. So this will be an example of a tile. So all squares must be covered in exact, and each square must be exactly once. And the question is, how many ways you have to tile the chessboard by dynamics? And well, for example, if you remove a certain cell, then of course no tiling exists because the number. Say, if you remove two cells on the opposite corners, again, there will be no tiling because this will be cells of same color, and then no tiling will exist because each diamond will have a different color. So existence of tiling is one question, and again, the number of tilings is very important combinatorial number, and permanent will appear immediately as counting. So the existence of tiling will be guaranteed by reason. So sizes should have a product which is an even number, and but if we start to compute it with recurrent rate, it will be quite difficult formulas. And again, permanent will just because permanent will represent stylings will exist for the chess. Well, I will not go into the details. There are different applications, distributed databases, physics, and so on. So permanent is indeed very useful. Let me then proceed by comparing it with determinant. So what do we have here? Well, we all know that geometrically determinant is an oriented volume of the parallelepiped formed by the rows of our matrix. Well, permanent has not such a nice geometric interpretation, but again, combinatorial geometry, which I already described, shows that it is important as a counting function. Algebraically, we all know that determinant is nothing but the product of eigenvalues. For permanent function, we have some bounds in spectral terms for certain special matrices. I will not go into details now. I will just point out that the feature which really shows these are completely different objects is complexity. So, by Gaussian elimination algorithm, we all know that determinant can be computed in polynomial time. And it's still an open question if there exists a polynomial algorithm to compute permanent. As of yet, we know some exponential algorithm. There is something because complexity can, by definition, complexity is factorial. And this exponential method of exponential complexity is based on Cayley-Weisel formula, which is nothing but when you multiply all row sums of your matrix, you will get some number which will be a little bit more than your permanent, because it will correspond to all possible permutations. And to obtain permanent, we should remove something from this product of row sums in some clever way, and this will be nothing but Cayley-Weisel formula, which has this exponential complexity. So, say, when we express, say, the number of dominant using permanent, well, it's nice, but the difficulty is to compute permanent. It's just difficult to compute permanent. Computing permanent belongs to so-called sharply complete class of problems in complexity theory. So before I will proceed with our results, I will try to give at least two explanations why it is so permanent and so different for the permanent. Well, first explanation is based on this Frobenius result. It's proved essentially in the same paper where he established the representation theory of fine groups. So assume we have linear and bijective transformation on complex matrices, which preserve determinant. Well, we all know that transposition is of this form. We know that similarity is like this. Of course, if you multiply by these two guys with determinant by product of 1, it will also preserve determinant. And the key result of Frobenius is that there are no more. Just these two types of transformations. And possibly by composition. And that's all. So this shows that transformations which will preserve determinant. There is a large class of such transformations which will preserve determinant. If we will look to the same problem for the permanent function, this is rather different. It turns such cases? Well, of course, there is another explanation. In determinant function, we have minuses in definition. And for permanent function, there are no minuses, which will mean no possible cancellation. So, determinant helps us to compute. And for permanent, we have to honestly compute each amount, which is possible another explanation. Why the difference is so huge? But, well, it was clear to ask, maybe we can somehow translate the problem of computing permanent in a certain way. We translate it to the problem of computing determinant in general. And he was inspired by, of course, by this 2x2 example. We put the minus in the southwest of here, and it will send permanent to determinant, and it was secure who showed that in general we can ask, is it possible to find a certain sophisticated way to put minuses in my matrix in such a way that permanent will be converted to determinant? So the result says no for n starting from 3. Yeah, for all n 3, starting from n equal to 3, it's impossible, and this is rather easy. Just take this matrix full of ones. Permanent is maximal, but determinant will be never maximal. An easy exercise. And then you just you can add a block diagonal. You can add a block of complementary size formed by identity matrix and 2 zero groups. And we will have example of for arbitrary n. For some families, if you don't want to convert all the matrices, but particular matrices, it's possible. For example, let's look at these guys here with 0 in the northeast corner. Well, there is a conversion, as you see. Or for Heisenberg matrices, again, this transformation will give you a rational converter. Or for the Jacobi matrices, again, if you multiply by imaginary unit, so not by minus 1, but by imaginary unit, you will still have conversion. Again, so this exercise is check with source. So one can ask in general, what will happen? What will happen with converters, those transformations which send permanent to determinant in a given class of matrices, possibly not all the matrices? Well, what will happen in the class of linear transformations? discovered these geometric obstacles for conversion and proved almost the same results as Marcus Aurelius. Well, there are many results in this direction. It's not my aim to mention all of them. For us, it was interesting to look at non-bijective and non-linear things. And since algebraic geometry arguments were working, of course, only over good fields, say at least we need our fields to be infinite dimensional, to have infinite cardinality. So what will happen over finite fields and for non-linear fields? Well, we started with few naive examples showing that there are converters. So this guy here will be a converter, which is of course non-linear, and it will be even a mixer. So it will send permanent to determinant, and determinant simultaneously will send it by this transformation to permanent. But of course it will be heavily singular. So what we do by good block and identity of complementary sets. Well, it's not a big issue to find a non-linear, non-singular converter over infinity. Just consider this filtration of our field in terms of slices of equal determinant and equal permanent. And then you just exchange these slices. And this local bijection will provide you such a converter. So it turns out that there are non-linear transformations, non-singular ones, but over infinity. What will happen over finite? At first, we were able to find a certain asymptotic result. So, starting from n greater or equal than b, it's always the case that there exists such a cardinality u0, cardinality of the field, so that starting from it, there will be no solution for this equation. No bijective map will satisfy this equation. Well, of course, for field of characteristic zeros, these two functions are just the same. Well, the idea behind is very direct. Of course, we do not have algebraic geometry over finite fields, but we can simply compute. For the determinant, remember this variety of matrices with determinant equal to 0. Over finite fields, it's just computable with cardinality. For permanent, this is open problem. Just how many matrices with permanent 0 will be over finite. Still open, but we were able to find some asymptotic ones. We introduced some recursive functions, Ln and Qn, satisfying this property. So, the cardinality of matrices having permanent 0 and determinant 0 were in fact divided by these bounds. And this is how we prove the result. This result, well, it's rather technical proof, appeared recently in the European Journal of Combinatorics. There were some consequences. For example, the question of Herbert's stability was to find the probability of a permanent to be equal to 0. This was done for 0-1 matrices in this paper by and we were able to obtain the corresponding result over finite fields from So we consider permanent of submatrices of our matrix. All these permanents of submatrices, and we put them in a certain tensor, satisfying some nice properties. And one of these properties is, first of all, we can describe permanent as such a tensor. We can find the Cauchy composition for the permanent one in this tensor language. And then the good thing was that it was possible to introduce such operation, a kind of convolution, a kind of tensor convolution of a tensor with a vector, which was able to do the job. And then it was possible to estimate in each product here, it was possible to estimate the quantity of current. Again, I will not go into the details, but as an outcome, there was a general result at the moment quite good. So over a finite field of characteristics different for arbitrary size of matrices starting for 2 by 2 case, we do have this nice example minus. First of all, the number of zeros for permanent is always less than the number of zeros for the permanent. When we first proved this result, I was asking the experts, finite fields or combinatorics, because it seemed to be, it sounds very classical, but it turned out that this was a new result. And of course, as a corollary from this result, it was possible to show that there are no contactors. So Polya problem for finite field was answered in negative for any bijective measure over any finite field, for any source. Well, this is one thing, but you may ask, Alexander, why you convert all the matrices? You can ask the same problem just for one matrix, just starting from completely opposite. What will happen with the Polya problem just for one matrix? Even if we restrict our conversion to be the sign technique, just putting minuses in a certain clever way into our matrix, which is Polya sign convertibility problem. This is again another well-known problem, which corresponds to many well-known combinatorial problems. For example, equivalent to even cycle problem, existence of cycle of even length in direct graph, science probability. I will not mention all these 30 equivalent problems. You can look at this nice survey paper by Matei just